Well, the bell just rang, so let's go ahead and go to All right. So yesterday we did a lot of different, like a variety. Shoot, I gave it away. Boy, that first bell just rang. Got an early start today. All right, so we like saw e to the 3x. Wendy, you asked about this.
Yeah, but now we're trying to talk about different. You're gonna have to go over another one too.
Oh, okay. E to the 3x, we found out like it's going to be e to the 3x times 3, which you need to get rid of that 3. So a 1/3 would do that, right? What you know it's going to have an e to the sine of t in it. So here's how you guess and check, okay? You know it has to have that part in it because e to the u is e to the u times d dx. Do you agree? So you kind of guess and then you check it. What's the derivative of this? Well, dy dt is e to the sine of t times cosine t. Ooh, beautiful. That's exactly what we wanted because of the chain rule. So isn't this like a reverse chain rule? We're going to have another process to solve this in the next section called u substitution. It's a more thorough way to make sure you get it right other than guessing and checking. All right. So, and there's going to be some complex ones where you can't guess and check at. So for number 8, that was the final answer. Right? Number 10. 10 was dy du. And 4, sine of u cubed times cosine. All right, guess and check. Well, I kind of look at this as another reverse chain rule. Do you guys agree if this was 4x cubed, wouldn't the antiderivative be x to the 4th? But it's like composite. So let's try sine of u to the 4th and see what happens. Isn't that derivative going to be 4, leave the inside alone, to the 3rd times the derivative of the inside, which is? And would you look at that? It matches up. So far in this section, what you just need to make sure you're doing is guessing and checking. All right. The worst thing you can do is not put a pencil to paper and just kind of be like, I just don't even know where to start. Like, try something. Look for what general, and I said this a lot in the first semester. What overarching derivative rule is this? Remember how I said that? Is it a power rule? Is it a chain rule? Is it a push? It's like the reverse of that. What overarching derivative rule did this thing come from? And it kind of looks like a reverse chain rule. So let's go backwards and think what was being put in the inside and outside to get there. Any other ones? Wendy. 7. All right. Any guesses and checks at this one? Wendy, what do you think?
Sine of t to the 3rd.
Let's try it. Sine of t cubed plus a constant. Let's take the derivative. Well, the derivative of the outside would be cosine. Leave the inside alone. And that's where remembering our derivative rules from way back, when we said take the derivative of the outside, leave the inside alone, allows us to now see this inside must have been left alone originally. So it kind of gives us a leg up on it. here times the derivative of the inside, 3t squared. Do we have a 3t squared? Yeah. And what if this was a 6t squared? Then we would need to put a 2 in front of this sign of t cubed, right? We can adjust for that constant. Are you starting to see the pattern here? Getting better? Any others? All right. I want to see what I assigned for homework for tonight. All right, 15, 21, 25 to 28, 15. I'm trying to remember where we left off yesterday. We did this one, didn't we? All right. Short lesson. All right. We'll have some time to. All right. So we did that one. Here is one I grabbed from an AP release test. Can you guys read that in the back? The slope field for a certain differential equation is shown above. Let's pause there. What did I say a slope field was used for? Huh? To visualize the antiderivative, right? Quick rewind. Here's cosine x. Here's 0. Here's pi over 2. Here's pi. Here's 3 pi over 2. Here we go. Cosine of pi. Cosine of pi over 2. When I plug in pi over 2, I'm going to sketch the slope. What's cosine of pi over 2? Huh? 0. So I sketch little slopes of 0. These are little tangent lines. 0, 0, 0, 0, 0, 0. Cosine of pi. So the slope is -1. -1, -1, -1, -1, -1. Little slopes at -1. If I did in between those values and I made them small enough, I would actually get these. Do you agree? If I did enough of these little slope segments and connected them, I start to see the sine curve, don't I? Because the sine curve has slopes of cosine. If I graph the slopes and I connect enough of them, I'm graphing the sine curve. Okay, so and not just the sine curve, but the sine curve, it's disconnected. But oh, come on. Plus a constant. It's all of them. I don't know which one it is. It's sine of x plus c. Sine of x plus c. Okay? All right, so what are we looking at here? We're looking at the antiderivative. All right? The slope field for a certain differential equation is shown above. Which of the following could be a solution to the differential equation with the initial condition y of 0 equals 1? All right, so what do you notice we're trying to find? The original. We're trying to match it with the original function. Here's what I would recommend. The first thing I would do is look at when x is 0 and y is 0. When x is 0 and when y is 0. When x is 0, what are all the slopes? All 0. Well, what's the sine of 0? 0. That's good so far. Okay. How about the second one? What's the derivative of this? -2x. When x is 0, the slopes are 0. How about this one? E to the x. What's e to the 0? That's not it. What's this one? -2x times 1. I don't know why I did it that way. Hold on a second. 1/2, leave the inside alone, to the negative 1/2 times negative 2x. So that 2 and the 1/2 cancel. I get negative x over the square root of 1 minus x squared. When x is 0, the slope is 0. That one's okay so far. Need a quotient rule for this one. Low, d high, minus high, d low, over low, low. So now we have the y's and we have the derivatives. There's two ways to look at it. One, does this shape I'm looking at match these y's? And two, do these derivatives match these slopes? Cool.
Why is E not tangent?
Oh, I took the derivative. I'm taking the derivative of it.
Tangent.
Yeah, the tangent inverse, or the antiderivative of this would be tangent inverse, but the derivative, the dy dx, is as a quotient rule. Thank you. What's the second thing that would be easy? When y is 0, the slopes are 0. All right. What else? What do all the slopes look like in the first quadrant? Positive, 0, negative. Negative. All in the second quadrant, positive. So when x is positive, the slopes are negative. When x, let's narrow that down right now. When x is positive, the slopes are negative. That's out. And we're looking at the green right now. That's out. When x is positive, the slopes are negative. But what gets rid of b here? I better be careful with that. Cole, go ahead.
I was going to say the slope square was 2, but that's wrong.
Okay. I look at that one and I say, for the same reason, didn't all of these have the same slope vertically? Why? Because when I plug in x and I get out a slope, they're the same slope for that x. Now, there's a little bit of a caveat to that, but we'll talk about it later. All right, next one. Let's look at D. When x is positive, the slopes are, the numerator is negative. What's wrong with the denominator? What's up? Denominator. When x is 1, when x is 2, when x is 3, 1 minus 4, 1 minus 9. Wouldn't have a derivative there, would it? Wouldn't have a slope there. What about the bottom one? Well, that goes away. Negative 2x over that squared. When x is positive, the slopes are negative. When x is negative, the slopes are, the dy dx's are positive. All right, take 2 minutes. Talk to each other. Try to narrow it down and see if you can figure out which one this is. They like, if this is on excuse me, if this is on multiple choice, they like to have process of elimination. Okay, process of elimination. You will see these in free responses as well. Is that enough? Yeah? All right. What'd you guys get? Yeah. So B is out because all the slopes should be the same vertically on for any x. D was out because when x is positive, you're not going to have a slope. But then I'll have students say, wait a minute, I thought you just said if there's x's, it's going to have the same slope vertically. And that's why I said there's a little caveat there. Okay. It's time. It's been a while. It's been a long time. All right. Time for the disguise. What do we notice dy dx is? Dy dx, are you okay if I write it like this? Negative 2x over 1 plus x. I'm not going to do that. Hold on a second. 1 over 1 plus x squared times negative 2x over 1 plus x squared. Let me double check. Is that legal or illegal to write it like that? Legal, right? So dy dx is negative 2x times y. Hold on a second. Negative 2x over, missed the part, 1 plus x squared. Wasn't this y? And isn't the rest this? So even though it looked like it was only a function of x, it was technically disguised and it had a y in it. What does that mean? That means vertically, the slopes aren't the same for any x because they're also dependent on y as well. So how do you find a slope? Well, you have to plug in an x and a y to get that slope. Okay? Do you remember doing implicit differentiation? Remember how there were, if it doesn't pass the vertical line test, there may be two different slopes for the same x because our derivatives were like negative 2xy. Remember how they had different, they could have two different slopes for the same x value because they depended on y as well. That's kind of what's going on here, okay? And the final thing, you should make sure that your pick goes through 0, 1. If I plug in 0 into y, plug in x equals 0, I get out 1. So it fulfills that as well. Okay? That was a little tricky. What you're going to see in some of your classwork are not quite as bad. Ooh, that gives away the answers. More matching. Match the following to their correct slope field. All right? And then if you're asked to graph a slope field, here's what the AP writers like to do in the book as well. You're not going to graph a slope field everywhere. You're only going to graph it at maybe 3, 6, 9, 12 indicated points. So here's how you do this. Let's pick one that's more difficult. All right, let's pick 31. If I want to graph the slope field using 31, I need to have an x and a y. Let's start down here. Negative 1, negative 1. When x is negative 1 and y is negative 1, I get negative 3. Do you agree? Negative 3. Well, how do I graph a slope of negative 3? Like that. Get close. Then I'll move up to this point. What point's this? Negative 1, 0. 0 for x, negative 1 for y. So there's a slope of negative 1. How about negative 1, 1? Negative 1 for x, 1 for y. What's that? Good. Negative 1. And negative 1, 2. 2 for negative 1 for x, 2 for y. 0. Slope of 0. That's how you graph a slope field. You plug in both the x and the y, and you sketch a little slope that has that. And I love the scoring rubric on the AP test for these. Okay? It'll give like 2 points, and it'll say 1 point. Positive slopes when x's are positive slopes, negative slopes. And like if you just had a positive little slope little tangent slope, you're good. It doesn't have to be like one steeper than the other one. Oh no, they're gonna get out a ruler and protractor, and they're not gonna do that. They're looking for, did you get positive slopes when it's positive, or negative when it's negative, zero when it's zero. All right. And they may ask you to sketch a solution curve through the indicated point. So what that would mean is at 1, they'd want you to try to sketch using these tangent slopes. Now, here's the little checkpoint. Are you ready? When x is -2 was my slope pretty close to their slope. And when x is -1 is my slope close to their slope. And x is 0 is my slope 0, yeah. And then over here, I was a little steep negative there, wasn't I? Okay, so try to get as close as you can. And then over here is my slope close to their slope. That's called a solution curve. It's a particular solution. It's the one that goes through the indicated point. They might ask you to do that. Does that make sense? Awesome. Solid class today, really. Okay.
Show us talking about our calculators.
Oh yeah, let's do it. Thank you for reminding me. 15. All right, number 21. You may call it the dirty rule. It's back to the FTC part 2. No, part 1, sorry. It's just your answer for 21 is going to have an integral in it. It's not going to have an antiderivative. You're going to have the integral symbol because you don't know the antiderivative of that. All right, good news. 25 through 28 is matching. Those won't take long. And then 30 and 32, you're going to graph slope fields at the indicated points. Do it in your notebook, please. Don't try to sketch it in the book.